The purpose of this lab is to understand how Faraday's law relates to changing magnetic field and can induce an EMF which drives current. This current can in turn produce a magnetic field and thus a magnetic force to oppose the changing magnetic field. In this lab, we will collect observational data of a magnet falling through a conductive tube of aluminum foil. We'll model the magnet-tube interaction computationally, and we'll compare the computational predictions with the observed data. Faraday's law shows how an induced electromotive force is equal to a negative change in magnetic flux over a change in time. We know that magnetic flux is equal to the integral of an area normal to a magnetic field. And Ohm's law shows us that current is related to EMF over resistance. We also know that magnetic force is the cross product of length and magnetic field times current. And this is the equation for magnetic field of a bar magnet. From Newton's second law, we're able to get the position and velocity update formulas. And Newton's third law explains how the induced magnetic field creates an equal and opposite force on the source of the original magnetic field. As a preview of the results, I found that the computational model predicted a time that was 0.32 seconds, while the actual experimental time was 1.314 seconds. For the initial conditions, I found that the system was the bar magnet and the surroundings was the aluminum tube. The bar magnet is positioned at the top of the tube with a zero velocity, and the tube is 1 centimeter thick with a 4.5 centimeter diameter and 46 centimeter length. For this experiment, I assume that the tube stays fixed and that there's no drag force, and that the gravitational force is negative mass times gravitational constant. After holding the bar magnet above the aluminum tube, I released it and measured the time it took for it to travel through the tube. I did this 5 times, arriving at an average time of 1.314 seconds. For the glow script code, I first set up the initial conditions, including the geometry of the tube and the magnetic moment of the bar magnet. I then calculated the magnetic field at position R relative to the bar magnet, using the equation for magnetic field of a dipole. Next, I calculated the rate of change of the magnetic flux through each ring caused by the falling magnet. Then I used Faraday's law to calculate the current induced in each ring by the falling magnet. I used the Biot-Savart law to calculate the force exerted on each current-carrying ring by the falling magnet. I then used Newton's third law to calculate the force exerted on the falling magnet by the whole tube of the current-carrying rings. Next, I calculated the net force of the magnet by including gravity. And finally, I used Newton's second law to create the position and velocity update formulas for the motion of the falling magnet. Using the magnetic dipole moment magnitude of 0.22 amperes times meter squared, the total falling time was 0.321 seconds. This time was shorter than what the experiment results indicated. Therefore, the magnetic dipole moment magnitude has to be much greater. Once I changed the dipole moment through trial and error, I was able to get the time of 1.314 seconds, at which the moment magnitude was 0.778 amperes times meter squared. We know that the red indicates a clockwise current and the blue indicates a counterclockwise current. If the line where the blue and red meet represents the position of the magnet, above that position, the time-varying magnetic flux is negative downwards, meaning the induced current needs to generate a positive downwards B field, i.e. clockwise, and vice versa. If we flip the magnet around, the colors then change, and the currents they represent change as well. Blue now represents a clockwise current, and red a counterclockwise current. As noted before, the total time in the tube of the real-world system was much longer than that of the computational model. To improve this accuracy, I changed the magnitude of the bar magnet dipole until the times were the same. Initially, the magnet accelerates downwards, but upon reaching the middle of the tube, the acceleration slows to 0. Finally, reaching the other end of the tube, the magnet begins to accelerate again. This tells us that the force of the tube on the magnet is greatest near the center of the tube and reaches equilibrium with the gravitational force for a short amount of time. What if the resistivity of the conductor were reduced to close to 0? In this case, the current induced would be far greater, and likewise the force induced on the bar magnet would be far greater, meaning it's possible that the magnet stops or is even repelled at some point, assuming the tube remains fixed. What if holes or slots were cut in the tube? Since an electric current is only induced on a closed loop, this would mean there would be less loops of current in the model, meaning that the overall magnetic force on the bar magnet would decrease.